right, so your written test number 2 will be tomorrow. And you already got a guide and also the example questions. And there will be an in-person session today. Actually, after when we finish our class, it will be around 2:20. Maybe if you can make it, feel free to take a lunch break. And then you'll be in the Ross Building North. And then second floor, 203, and 3 p.m. So we just go over the practice question on the e-class. And then if you got any follow-up to any of the questions, I'll be there. Tia will be there. We can answer you, right? If you can make it, that'll be great. If no, I'll try to also make the recording available to you, but it may have to be quite late today because I finished my last class quite late. But I'll try my best. But you'll be the best if you can come and then just get the doubts sorted out as early as possible. I think that'll be your best interest. Anyway. And then you have the notes on typecasting. So that will be the PDF note I showed to you last week. So take a look. It's also on the lecture site. It's going to also complement your study for the the test coverage. Just to remind you very quickly, so we were up to slide number 67 for the inheritance lecture. That's the last example we did from last Thursday. So that'll be the final slide you have to study until. Today we're going to cover some new stuff. I think to really build it up, we can actually usefully review certain stuff that you have to know for tomorrow. So we can definitely do that revision as well. And then another thing that's kind of optional, same deal as your midterm course evaluation. So if you're interested, so this will be the online course evaluation that's official. I send the e-class announcement. You can just follow through the link. I'll send you some reminder as well for your early participation until Thursday. Okay, so it's really up to you. I don't see any result of that until middle of January. So it's way after the final grades will be submitted. So just express yourself freely in the evaluation. Okay. Guys, any questions? Before I do some quick recap, and then we'll talk about some stuff. Okay. All right, let's now recap from last time. Okay. So last time, basically, we talked about typecasting, right? Of course, we first started about polymorphism, dynamic binding, and we'll develop polymorphism even more. We'll do a little bit today just to pave the foundation, especially you got polymorphic array. That's something we'll dive into more details on Thursday. Okay, polymorphism, dynamic binding, especially dynamic binding, about tracing which version of the methods is going to be called is something you have to know how to trace for tomorrow's test. And we talk about why we might need a typecast. You want to somehow work around the limitation of the compiler, right? So if you're pretty sure about the dynamic type for the objects, you can somehow cast to it somehow. Okay, so we talk about all the different examples. And this page here is only for your knowledge. Since for you guys actually are in the engineering major, you don't really take that 2001 course. So I cannot assume any knowledge about undecidability. But this page here, just for your knowledge. And then we talk about the syntax for the cast. And this is definitely something you will want to know, maybe also for your last programming test as well. I'll give you the guidance and also some practice tests, most likely tomorrow or maybe early Thursday. So you can also get prepared for that. That'll be the last one for the semester. So we talk about how you can visualize about the cast syntax as well. And just various examples. And also, if you do anonymous cast, you want to be careful about putting some extra parentheses to force the order of evaluation. Okay. And there are two dimensions for typecast. Dimension number one about compilable. Either you do upward casting or downward casting. Okay? So given the static type, you can either do upward or downward to ancestor or to one of the descendants. You don't consider any dynamic type just yet. And then we also talk about the possibility of something called class cast exception right here, right? So basically, that's something we'll have to revisit again today. So when can you have the class cast exception? When the dynamic type of the object you're trying to cast right here, for example, dynamic type for that, cannot fulfill the expectation of the cast type. That's exactly the condition we're going to have class cast exception. Okay, just got to pay attention to it. And we'll build something similar around this today as well. Okay, and then we talk about example. And this page here is also very important. So given the static type and dynamic type of some variable, you can now categorize all the classes in the hierarchy for the inheritance into either compilable versus non-compilable cast, and also exception-free versus those that's going to give you class cast exception, right? So just be careful about how you can derive these classes. Okay. And then that's the last example we did. And the main lesson we learned from this is, as far as compilation is concerned, you can cast one class into, you can basically class one type into another arbitrary type. All you got to do is do some upward cast and downward cast. But you still got to pay your price. You may still have class cast exception at the runtime. So for the example we did last time, you want to trace very carefully about where exactly we actually got the class cast exception. Since we got two casts in a single line, which one actually triggered the class cast exception? All right, so watch out for that. And then just one example about doing some multicast in a single line. All right, guys, any questions from last time? Anything you want me to clarify before I kind of move further? Okay, so today we're gonna first talk about a new operator. And I know for your lab number 4, many of you actually have been doing the right thing. I kind of expect that by using the getClass method, which we kind of did in the object equality to really figure out dynamic type. It's completely okay, right? You can do it and then pass the test cases without any problem. But today I'm going to show you another operator, which you still have some time to really get a chance to revise your lab number 4 if you want to. Otherwise, you can do it even after submission deadline. So there is an operator called instance of operator. One moment. The instance operator is going to be used closely right before whenever you want to do a typecast. It's more like a safety guard you want to do. Patricia, question.
I wanted to ask the difference between instance of and getClass.
Good. I would love to answer that. How about we go over maybe the instance of example first. Maybe after we take a break, remind me again, and I can talk about it very briefly. Okay, good. Yeah, let's learn about instance of operator first. Okay. And by the way, so instance operator is not covered tomorrow, right? So don't panic, right? So just learn the stuff and get used to it, okay? Today could be a little bit intensive again, because we got many examples to go through, okay? But as usual, stop me whenever you need to, okay? Let's now start with some very quick walkthrough about the syntax and also what you need to know in a summary, okay? Like a cheat sheets in some way. So the instance operator, okay, is a single word, instance of. Instance of, right, is a keyword in Java. Okay, instance of. It's a binary operator, meaning that there should be a left-hand side, and there should be another right-hand side right here. And it's a Boolean operator, like a ampersand, or vertical bar. It's going to return either true or false. Okay, let's see what should be on the left and what should be on the right. And then I'll give you some intuition about how you can understand about instance of. The word itself is not that intuitive to understand exactly what's going on. But I'll give you something that's going to be consistent with how we have discussed the intuition for inheritance. Okay. On the left-hand side, usually it's going to be some expression. An expression. Denoting some objects. Okay, example. The simplest one you can put is simply just a reference variable, which denotes some objects because it stores an address. Simplest one, you can just put some variable x, or more commonly, maybe for your lab number 4, you can put some array indexing expression. You might say array A, and then add index I. For example, maybe array A stores an array of followers, in which case AI might denote maybe some follower, which can be subscriber or monitor, right? That's back your lab 4 context. So let me just put X right here. Okay, just some object expression. The right-hand side is actually quite simple. It's going to be just a class name. Let me say Y. A class name. Of course, it has to be known. Okay, has to be a known class name. So how do we understand this instance of? Okay, let me put down something that's consistent with how we have understood inheritance, especially the rule of substitution. When I say X instance of Y, thinking the following way. X can dynamically fulfill the expectation of Y. That's what we're thinking. All right, I'll put it down. X can fulfill dynamically the expectation of, right? So here, X can fulfill dynamically the expectation of Y. And in this case, if that's true, return true. Otherwise, false. Okay. And of course, since we say dynamically, that means we consider dynamic type, right? Very important. Okay. So here, whenever you want to evaluate the instance of, if you talk about runtime either true or false, you have to consider the dynamic type of the X. So far we talk about ST stands for static type. DT stands for dynamic type, right? That's something we have been using throughout the lecture. So now, again, just like how we discussed about typecast, you have to talk about two dimensions. Either does the cast compile, or what's going to be the runtime behavior, 2 dimensions. Similarly, for instance of. Let's talk about compilation first. Okay, let me just talk about compilation. Okay, the rule is very simple. So you want to understand instance of together with the cast that we learned from last Thursday. Okay, this is how you understand it. X instance of Y will compile. Compiles if and only if, which means the opposite side, or the other direction also true. Okay, compiles it if and only if the cast of X into Y compiles. Okay, so now this is something we are very familiar with, right? So if I try to cast some object expression X to Y, class Y, when does it compile? When we try to do either an upward cast or downward cast, right? Okay, it's a reminder. Either upward or downward cast. Okay, and usually this Y over here will be used verbatim, usually. Used verbatim, which means you just use Y directly. You don't really try to choose maybe its ancestor or descendants. Just choose Y precisely. Verbatim in a subsequent. I will explain what subsequent really means. You'll see the example. I'll just say subsequent for now. In a subsequent cast. Okay? All right? So far we talk about compilation, right? Whenever you see the instance of expression, think about what would be the corresponding typecast you're going to write. If that typecast compiles, the instance of should compile. Okay? We'll see some example very soon. Okay? So that's about dimension 1, compilation. What about dimension 2, assuming that the assuming that the instance of compiles. At the runtime, there are only 2 possible outcomes. Either you get true or you get false. All right? So the next dimension, at the runtime, instance of evaluates to a Boolean result. Okay. Which will be either true or false. And this intuitive description, they already gave us some hints about under what circumstances are we going to evaluate the instance of to true. Okay, let's see. Okay. It would be evaluated to true if the following. Okay, let me just say true. True if. And there are at least 3 possible ways to really phrase the condition. Let's go over all 3 of them. So the 2 of them, you can use ancestor, you can use descendants, but I would say if you're still not exactly comfortable about using these terms, you may want to start with a more intuitive notion about the condition. Okay? It will be true if the dynamic type of X can fulfill the expectation of Y. Precisely that. That's exactly the intuitive description I just said. All right? So number 1, dynamic type of X can fulfill expectation of Y. All right? And given 1, we can now try to play with the ancestor and descendants notion quickly. All right? So that means you can say if this can fulfill the expectation. That means this must be a descendant of that, right? Dynamic type of X is descendants of Y. Or conversely, Y is ancestor of the dynamic type of X. So we are really just, the important thing is about dynamic type of X, dynamic type of X, dynamic type of X. Give me one moment. Yeah, let me just finish this and I'll take a question. Sorry. And then fulfill expectation of Y, and also Y, and also Y here. Yes, question?
It's not like a class itself or an object. For example, do you put is essence of, for example, another object, or you have to say only class name?
Right. So the left-hand side is going to be some expression denoting some object. Could be X, could be some array indexing. The right-hand side, just a class name.
You cannot do anything else.
You cannot do anything else. That's correct. Yeah, good. All right, good. And then otherwise, if this condition is not the case, for example, if that cannot fulfill, then otherwise it would evaluate to false. Okay. Oh, sorry. Okay, false otherwise. All right, let me say one more thing that's actually important. So now let's draw some connection from why are we learning about instance of? The reason is we know that when you try to do typecast, even if the typecast can compile, you're still under the risk of having the class cast exception at the runtime. So it's better to actually check it before you actually do the typecast. Let me write it down first, and then I can give you some practical tip. All right. The final remark goes like this. If the instance of, you check right here if it is true. If true, okay. For example, if this one here is true, that means I can safely cast X to Y. All right. If true, then it is safe to execute the cast Y and X. Okay, this one here. This is very important over here, and this should be kind of related to right here. Okay. Okay, and when I say safe, okay, safe really means no class cast exception. No class cast exception. All right, let me recap very quickly, and then I'll take question. And we got to do example. So what we're saying is, for this binary operator, it's called instance of. You put some object expression, you're asking, can the dynamic type for that object fulfill the expectation of this class name Y? If that's true, that means you will be safe for you to cast that object expression to Y without any trouble, without any class cast exception. So typically, you want to do the instance of check before any typecast. You're not exactly certain. On the other hand, you don't necessarily have to check every typecast by using instance of. You don't need to overkill, right? It's more like a balance you have to strike. So for example, you don't really have to check if the context object is equal to null before you make a method call every time. You don't have to, but sometimes it might be safe to do so. So you got to strike a balance. Exactly what should be the balance is not something we can really teach you in this course. You have to gain some experience to see what kind of pattern you'll be more exposed to such risk. So I would say that's kind of beyond the scope for this course. For this course, just make sure you understand exactly what instance of really means, and then how we can combine that together with the typecast that we're going to follow. Okay, I think that's the main lesson. Let me do one more diagram here. Okay. So think about this X over here is more like an object, right? So let me just say X is pointing to some objects, and then with the dynamic type, so let's say X is dynamic type, right? Could be something. And then instance of Y. We are basically asking, can this particular dynamic type fulfill Y? So that means Y should be somehow higher in the hierarchy. Otherwise, it cannot fulfill that. If Y is somehow lower, or it's neither, it's not the descendants, in that case, you cannot. Okay? So graphically, you can think about if this is dynamic type. So that means if you follow through its ancestor path somewhere, you're going to see Y. Okay? If you can imagine the inheritance hierarchy. All right? Because you can only fulfill your own ancestors' expectation, not lower. Okay. All right, let's now do one more. How about we do some example quickly, and then we generalize it. Quick example. Let's now take a look at just this one here. Okay. And this time, let's try not to visualize the objects, like per line. Let's see how efficiently we can deal with this. Okay? You just have to identify the relevant classes in the diagram, inheritance hierarchy. Okay? So what we have is we have some static type students right here. And then the dynamic type is non-resident students right here. Oh, sorry, right here. Non-resident students. So this one here is a static type. And this one here is dynamic type. And we know pretty well this rule of this substitution will compile because this is a descending class of that. Okay? For now, ignore these two lines for now. Okay? How about I'll just delete them just for now. I really want to make the point. For now, you can simply just ignore these two lines. I'm going to put them back very soon for now. All right? If you only look at line number 3 and 4, that's something we know from last Thursday. All right? So now what we're doing is we are trying to cast Jin to resident students. And let's do a little bit of review for tomorrow, right? If you look at this one here, you're basically asking two questions. Number one, does it compile? Let's start with this. Did this one compile? Are we doing upward casting or downward casting? No. Downward casting, exactly. So Jin, statically, students. You're cast into resident student, downward casting. Very good. Okay, it's downward casting. Since it compiled, we can ask the follow-up question. Okay, so meanwhile, I'm just going to put resident students right here. So that one is the cast type. Okay, so now question number 2. At the runtime, when we execute this cast, are we going to run into class cast exception? I'll let you. Yeah. Yes, because?
Because it cannot fulfill the expectation.
What cannot fulfill what?
Resident student cannot. Student cannot fulfill all the expectations of resident student.
Oh, not quite. You talk about static type, right? Remember, class cast exception, you have to consider only dynamic type. Be careful. So guys, today, if I ask you any question, feel free to try. It's okay to be wrong. This will be a nice way to rehearse for tomorrow. You'd rather be wrong today in class. Okay, go ahead.
Non-resident student, but they're trying to cast to a resident student, which is not a descendant of resident student. That's
Yeah,
why I'm saying.
that's good. Very good. Okay. So again, whenever you want to decide whether you got a class cast exception, right? You look at the dynamic type of Jin right here. And can this fulfill the expectation of resident students? So is this a descendant of resident students? No. So class cast exception. All right. Let's write it down. Class cast exception, because dynamic type non-resident students, not descendants of the cast type, which is resident students. Right, so we know pretty well, line number 3, if we are not being careful, we might get a typecast to compile, but we're going to run into the class cast exception. So this is where the instance of can be very handy, because every time, if you want to be sure the cast is really safe, you have to make sure the dynamic type can fulfill the expectation of the cast type. That's exactly what the instance of operator will check. So let's now remove these two. Put them back. All right? So now I'm going to highlight these two things. So it will be here, okay, surrounded by basically an if block, right? If the branching condition there is actually false, we wouldn't actually bother to execute these two lines. But let's see if that's really true or false. All right. So now let's try to look at this line over here. Right. This line here, it boils down into can Jim's dynamic type fulfill the expectation of resident students? And notice that resident students over here, let me highlight, emphasize it. The resident students over here is exactly the type we want to use as a cast type. That's what I meant. Usually for the Y over here, you want to use it verbatim in the subsequent cast. Because if you're able to reach that line, that means the instance of check already passed for that particular class for cast. All right? Okay. So can it? No, it cannot. All right? So this one here will be no. So that means it is going to return false. The reason no is dynamic type right here. Can it fulfill resident students? No, right? The same question, really. Okay? So since we get false, so that means this part over here is going to be bypassed. Bypassed. Which preventing the class cast exception from happening. All right. Any questions about what we're doing here? We're basically just adding an extra layer as a safety net. Whenever, well, let's go with one extreme. Every time before you try to do a typecast, always make sure that particular typecast not only compiles, but also is not going to run into any class cast exception. That's what we are ensuring. And always do instance of check. Okay. All right, any questions? Okay. And there's another one here. I'll leave that as exercise for you. You can also see the answer on the slides. Okay, exercise here. Okay, give it a try. The reasoning pattern is going to be very similar. You can try to do something that I just did, right? Try to cover these two lines over here, and then try to analyze these two lines, and then try to see how the if condition here can prevent any potential class cast exception from happening. Okay. All right. If no question, let's now generalize what's happening here for instance of. Right? It's not too bad. It's very similar to how we argue about the category of classes when we talk about typecast. Okay. Oh, another thing, maybe it's better, I think there's something kind of learned from the presentation yesterday for your section B fellow student. Let me talk about this one first. Okay. If I say, let's say X instance of Y. All right. Okay, now I know exactly what I want to do. Versus if I say cast X to Y. Okay, I think that's all I need. Okay, let me do better. Let's now consider these two expressions executed separately. All right, and then let me give you some condition. Okay, the condition goes like this. First of all, dynamic type of X can fulfill the expectation of Y versus it is not the case, right? Logical negation just means it's not the case, right? Not the case. Dynamic type of X fulfill the expectation of Y. Let's now try to think about what the consequences are for these four. All right, for these four. Let's start with something we know, typecast. Why don't you help me with, let me put this back. Let's start with this one here. this one will succeed, but doesn't return anything. You just create an alias, right, for the typecast. So this one here, the typecast succeed creating an alias of static type y, right? Like what we said earlier.
Should we first check that x is the static type is itself right that we reach this?
Oh yeah, of course. That's something. I'm more like a past. Okay, how about this? It's a very good concern. Let's say we assume both compile. How about that? I just want to save that discussion. Yeah, that's a good point. Assume both expressions compile. And of course, there could be some extra exercise for you guys to try. What does it really mean for both compile? All right. So this compile and also this compile. Okay, assuming that. All right. What about here? What's going to happen? It won't succeed. And what's going to happen? Class cast exception. All right. Okay. Good. Awesome. Class cast exception. All right. That's good. And now let's see. For the same x and y. So now let's do instance of check. What about this one here? True. All right. Very nice. And are we going to get class cast exception here? No. What do we get? False. Okay. So now you can see these two notions are closely connected, except you should really try the instance of check to make sure if it is false, you just don't execute whatever that's inside the branch for if, so you can avoid the class cast exception.
Can I sort of something like instead of using try and catch, so we'll try and if class cast exception,
Yeah.
catch it, something like this.
It's something like that, yes. But just in general, because instance of is like a Boolean operator. You can simply say if instance of something, and then you can throw some exception or do try and catch. Yes.
I mean, you can implement in instance of as a function using the other one.
I wouldn't go that far. Yeah, I think there's such a high demand that you need this kind of check. So that's why they provide with you, this operator. Yeah, if you want to implement something similar, yeah, sure, it could be a nice programming exercise if you want to. Yeah, good. All right, guys, it's a very important summary comparison. Okay, I'll leave to you. Just think about it. Okay, just convince yourself. Okay, having this said, let's now generalize the story for instance of. All right. Let's look at this diagram right here. Okay. We choose. Okay, so let's look at this line here. Oh, sorry. Let's look at this line. This line here. So we basically got static type A, and also we got dynamic type B right here. And this one should be good because this is a descendant of that, the rule of substitution. And a very quick reminder. If you look at A here, A is the static type. If I want to do a typecast that's going to compile, it should be either upward cast to any of the ancestor, or it can be a downward cast. As you can see, the descendants of this particular class is going to contain all these classes, right? So all these classes over here can be the class I can compile into without any compilation error, either upward cast or downward cast, right? Of course, this one here is neither ancestor nor descendants. In that case, I cannot do any typecast. It's not going to compile. Okay. So what we want to do is, we want to look at this one here. Okay. If you look at this line, obj instance of. Okay. First of all, let's talk about compilation. And a reminder. This compiles if and only if when you try to cast the obj to some question mark. We want to figure out what will be the range of classes that can replace the question mark. If and only if this compiles. What will they be? Could be upward cast or downward cast. So it's going to be basically like this. Okay, let me try to see a highlighter. That might be easier. So it's going to be basically anything in this range. All right, so these are the classes that's going to make the typecast compile. On the other hand, these classes right here is not going to compile. These classes right here, okay, right here, they are neither ancestor nor descendants of A. The cast fails to compile. Okay, dimension number one, just about compilation. Okay, dimension number two, out of those classes inside the blue highlighted area, those classes, which ones is going to somehow, number one, makes the typecast exception free and also make the instance of check true, right? They are the same condition really, right? In that way, we have to look at the dynamic type. Any class that can be fulfilled by dynamic type should be good. That means dynamic type's ancestor, okay? So this way, I'm just going to highlight it. So it's going to be, okay, let me just do a little bit thicker. It will be dynamic type itself, which is its own ancestor. And also another ancestor here, another ancestor over here, okay, another ancestor over here, all the way to the top of the hierarchy. So these are all the ancestors for the dynamic type. So all these classes, not only that it will compile for the typecast, but and also instance of, they will also be sure there's no class cast exception. Okay? And also the instance of check will give you true. Okay, I'll put it here. So all the purple one. So these classes will, number one, not cause class cast exception for the cast. Number two, make the instance of check evaluate to true, right? So basically, I'm talking about this question mark here and the question mark here, right? You can see I somehow choose them to be the same. Okay, so I think that this table here is actually very important, which I just did. Right? I think this kind of based on this table here. Okay, let me say it again. Given that I have static type, dynamic type, these two classes, in order for the instance of and the typecast over here to compile, it should be either an upward cast or downward cast. Right? In that case, it's going to be any of the ancestor or any of the descendants right here. So that's a blue area right here. So any of these classes can be replaced for question mark and make the instance of and typecast compile. Dimension one. Dimension two. Out of all these classes, only certain ones can really make sure we don't have any class cast exception or make the instance of check return true. How do we do that? We got to make sure the dynamic type can fulfill this particular class's expectation. So that means this class must be the ancestor for the dynamic type. So it's going to be the dynamic type itself or all its ancestor all the way up to the top of the hierarchy. All right? And all the other classes, for example, let's say this one here, also all these classes here, the gray one, and also here. All these classes, they will compile, but they will give you the class cast exception. And also instance of will be false. Okay, for all these. Number one is going to be class cast exception for cast. Also, it's going to be false for instance of check. Okay, again, you really want to base what I'm talking about right now on this table here, right? That's why I talk about this table first, okay? Any questions? So just one moment. So not really for tomorrow, of course, but for the exam. So that means I will definitely expect you guys to really understand very thoroughly about the connection between the instance of and also typecast. They definitely work very closely together. Question?
I get that the instance of works similar to like the class casting, but intuitively, when we think of instance of like, why wouldn't it work with a class from outside, like the family tree, like the ancestors or the descendant? Because it's like from the name instance of, you intuitively would think.
I know what you mean. So that's why I said earlier instance of simply means right here. I know exactly what you mean. Okay. So when you look at this word again, right? I think this word can be misleading, really. So what it is really saying is, can the dynamic type of OBJ fulfill the expectation of this particular class? And this class will have to be somehow relevant to the hierarchy that you're talking about, right? Smartphone, or maybe, I can tell you the only exception is maybe the object class, because object is implicitly the ancestor for every class. Yeah. Yeah. So of course the inheritance hierarchy here must be as complete as possible so you don't miss any important classes. Yes, question?
Something like this happens in example. I say 3 will give me a class exception, or do I say that it will not even go to this line, because if it fails, it will be false, it will not.
That's correct. Yeah, so I'm more thinking about, well, this is more like this table here. I'm more thinking about evaluate these two in two different execution runs independently, so we can see exactly what's going to happen. So in order to prevent this from ever happening, you better check this one first, because false is not like an exception. It's more like a value that's going to direct the execution flow at the runtime. Yeah. Good. All right, guys, think about this one here. If you have no further question, I think I thought it's pretty clear, but you just need some time to digest. All right. Exercise, and then how about we take a very short break? I still have like one or two sets of a very quick example, and then we can do some call by value, revisit. All right, let's now take a quick attendance. Let me get back to Patricia's question just before the break. So now that we understand about the instance of operator, let's try to compare that with the get class operator, right? Back in the object equality lecture, okay? I'll go straight to the point, okay? So what they actually share in common is when you actually try to do x.getClass, right? That one there is going to give you the dynamic type of x. And when you say instance of, you also have to use the dynamic type of x to check. That part is really the same, okay? However, when you say x.getClass right here, you're saying that dynamic type of x must be exactly y. No other flexibility, got to be exactly y. However, when you say x instance of y, you're basically asking, can x's dynamic type fulfill expectation of y? In which case, y can be very far ancestor. But if x can fulfill y, can x also fulfill the earlier or closer ancestor as well? Of course it can. So that's kind of the difference. So you do actually have some range of classes that's kind of implied by this. So I'm going to put it down here. So we basically think all these classes before y. Okay. X instance of y evaluating to true implies that x's dynamic type can also fulfill these closer ancestor. Okay, I'm running out of space. Ancestors. Okay, does it make sense? All right. So think about the difference between these two, get class and instance of. You definitely have to know when to use which. So when you want to give some flexibility, in that case, you definitely want to use instance of. Otherwise, if you want to say precisely it has to be this particular type, then you can feel free to use get class. But I would say you can stick to the instance of whenever possible. Patricia, does that make sense to you? Okay, Sounds good. Okay. Let's now do more example quickly, and then we're going to move on to call by value. Okay. Very quickly. Okay. So let's talk about this, right? We got a series of instance of check right here. Okay. Instance of. The left-hand side, all the same, just my phone. Okay. So you can see my phone right here. Okay. If you look, my phone here has a static type, smartphone, right here. The first question is, do all these instances of check compile? Do they? How do we judge? I kind of highlighted exactly what you need to know to really decide. Compile? Yeah, okay, I'll just get to the point. Because to any one of these, for example, Android here, Samsung here, all these classes, you'll be relative to the static type here. It's more like a downward cast for all of them. So they will all compile, right? All compile. Okay, so think about all the instance of compile. All of them compile because it's more like a downward cast from the static type smartphone. All right?
So instead of is like a downward or upward cast, you cannot go upward and then downward or something like this. For example, if
Yeah, it can be, a single instance of is really up or downward. Oh. Yeah, if you want to do multiple, you got to combine them, right? Yeah, I wouldn't go that far for now. Okay. All right, and then let's now decide each one of them, all right? So now question, before that, you can also highlight the dynamic type, which is Samsung, right here. All right, now we got everything we need, okay? So when I say my phone, that instance of Android, which is here, true or false? True. We're basically asking, can dynamic type here fulfill Android? It can, okay, so that should be true. So that one there should be true. And instance of Samsung itself, also true. It can fulfill itself. Can it fulfill Galaxy S21 Plus? It cannot, right? Here, it's not a descendant class of that, right? It's going to be false. So that way, we can somehow prevent class cast exception if you got any subsequent cast. Okay. Similarly, iOS right here, false, right? This cannot fulfill iOS. False. And also iPhone 13 Pro right here. So this dynamic type cannot fulfill this one here. So also false. Right? Instance of. Right? And then the next one is basically saying, so now we simply try to do the corresponding instance of check, just some of them. So let's say we got, let's say one here. I got another one here, okay? And then I got another one here, right? And notice that I deliberately choose this right-hand side type the same as a cast type. You can say this, you can see this type over here, and the same as a cast type that follows. And this type over here matches this cast type over here, right? It's deliberate. And then we're gonna look at what's gonna happen for each one of them. So they all compile. You can double check again, right? I'm gonna skip that stage. So what we do is, you can see dynamic type is Samsung, right? Right here. So now, instance of Samsung itself, true, right? In that way, we can actually do the cast. That means this will be no class cast exception. That'll be okay to do. On the other hand, can Samsung fulfill Galaxy S21 Plus? No, it cannot, right? As we said earlier. So this is going to give us false. So this whole thing here is going to be false. That means this is going to be bypassed, preventing the potential class cast exception from happening. All right? And also we have, how about this one here? Huawei, this one here, right? So this cannot fulfill that, right? Obviously, right? It's not descendants. So this is also going to give us false. So we also bypassed. So class cast exception prevented. Just more like a combination of the instance of and the corresponding cast. Okay. Okay. Just another quick serious example quickly, just to play with the static type a little bit. Okay. So here we have the context object SP right here. You can see for SP, we just want to check for compilation only. The static type is smartphone right here, smartphone. We know that expectation will be only dial and surf web. Only these two will compile. So dial, but other than dial and surf web, this will not compile and this will not compile. Okay, as easy as that, right? And then another one. This one here, we got iOS as a static type right here. And then iOS has the surf web, FaceTime, and also dial. These are the only methods we can call on iOS, right? So here, so that means dial is good and FaceTime is good, but no quick take. It's kind of beyond the expectation, right? It's quick take, right? It's not going to compile. Next one. And then over here we have iPhone 13 Pro right here. Okay. And then the context object, right? So here we got way more. You can see we got quick take, we got surf web, FaceTime, and also dial. So they're all good, right? Compiles. I'm just playing with the static type, basically. I just want to remind you, whenever you want to judge for compilation, you only look at the static type, nothing else. Okay, I believe one more. Okay. Yeah, one more, two more, quickly. So this one here, just about anonymous cast, really. So here we have, let's say, the same cast right here. We are trying to cast SP to iPhone 13 Pro, right? Right here. So SP has the static type smartphone, which is here. And then we are trying to cast to iPhone 13 Pro, which is right here. It's a downward cast, right? The cast will compile. The cast compiles. And once it compiles, the expression has the static type iPhone 13 Pro. In which case, we will be able to call all the methods from iPhone 13 Pro. Right? That's also something we said earlier. So after you have done the cast, the static type for that cast expression will just correspond to the cast type right here. Okay? So all these are also fine. And of course, you can also do as exercise to determine if we're going to have any class cast exception at the runtime. You can double check as well. Okay? Okay, one more, final one. And then we'll do something new. And this one here, again, just showing anonymous cast. Okay? So this one here, we're saying that we first of all do the instance of check right here. Okay? So we know that this will be true if it is safe to cast S to resident students, right? Can S dynamically fulfill the expectation of resident students, right? That's something we said before the break. So given that we are able to reach to the branch, so it would be safe to do this one here. And also, it would be also safe to do this one here. Both are safe. Safe, guaranteed. Safety, guaranteed. Because the instance of check evaluates to true. All right? It's just about playing with the check and also the typecast. All right, any questions? So that's about all I want to talk about instance of for today. We can revisit this maybe a little bit later just to see more examples for instance of. Right? In the next 20 minutes or so, let's talk about something relevant to what we spoke about earlier about call by value. A question.
In general, can you try to create objects or class objects dynamically? It's not, I mean, I don't mean by dynamically, you do if statements and then you check then you class. I mean, dynamically, you create, for example, the class as a parameter and then you test it. somehow like.
Oh, you mean when you pass, when you want to pass an argument, pass a cast version? Is that what you say?
No, not cast version. Cast the class name you want to cast to, not the string. The actual. Can you actually do this? For example, class resident student, and then cast to resident student.
I don't know what you mean. So why don't we talk about the idea after class? Yeah, I'm just not exactly getting. If you're only talking about, well, how about we discuss this after class? I think that'll be better. Yeah. Okay. All right. Let's now talk about do a quick revisit about callback value. Okay. And then we'll see how the callback value can, how inheritance can play some role in the callback value. All right. Let's revisit the idea. So callback value. Okay. Okay. So callback value is going to happen for every method call. So we got caller, we got callee. So let's talk about caller, callee first. The method being called. Let's say we have some callee over here. Let's say we have a class C, and then we have some method, mutator, let's say, M. And we have some parameter, let's say T1, okay, some type, some class name. And then we have some param, okay? And then here we can just use a param. The body of the method is not important, okay? And let's say we also got another side, the caller, who's gonna call the method. That one there is going to be a caller. And then let's just put a few lines of code right here. So that one there we got C, OBJ, new, C. Okay? And then we're going to say T2, some arguments that we're going to pass will be some initialization. And then we're going to say obj.m, which is this method here. And then we're going to pass arg. Okay? So we're basically concentrating on this caller callee. One here and one here. If you recall callback value from before, what kind of variable assignment are we doing? Are we doing param equals arg or arg equals param? Yeah. Okay, good. Okay, just make sure the order is right. Otherwise, the rule of substitution will be argued in the wrong way. Okay. So if you consider these two, all right. So we talk about callback value. It's going to be the param equals the arg. So this indeed is a variable assignment. What if the T1 and T2 involved, they kind of represent two classes in the inheritance hierarchy. So now we are back to the rule of substitution that we can judge, which we know how to decide, right? So now under what circumstances is this equals going to compile? That's the question, right? So I'm going to answer that, right? It kind of, so here we got to look up the static type. For param, the static type is T1. And for arguments over here, the static type is T2. Okay, so now we can work out exactly the rule. Okay, let's just write it down. Okay, so the rule of substitutions. Okay, so I'm basically referring to this variable assignments. All right, so you can think about two ways. Either you can think about the T2 must fulfill expectation of T1, right? Intuitively. T2 fulfill expectation of T1. Accordingly, T2 must be a descendant of T1. Of course, you can say T1 ancestor of T2. You can say that too, right? I'll just put 2 over here. Right, that's very important. So this one really is a foundation for us to understand whenever you got method call, where the argument and parameter may be somehow related to by inheritance. You have to know how to judge. That's exactly the mental model you want to have, okay, about callback value. Okay, let's see some example. So we are looking at some slides right here. So we've done quite a lot so far today. So I'm going to start you with right here. Okay, so all these have been done. Okay, so we're going to look at slide number 77. Okay, so slide 77. Let's now look at this class here. We have a class called Student Management System, and we have an array of students. And remember, student here is one class in the inheritance hierarchy. We got students, resident students, and also we got non-resident students, right? That's an array, okay? Let's start with this, and then play with some rule. Okay, for now, just look at this particular array declaration. The fact that statically, the array is of type students. What that means is each element in the array, index 0, index 1, index 2, all the way to the last index, has the static type students. Each element of array has static type students. It's a very important thing to really recognize right away, right? Statically declared. All right, after that, you can see we also got some method here. We got add rs, in which case parameter type rs has a static type resident students. Add nrs, another method, the parameter type is non-resident students. Also, we got add students, parameter type is students, right? We just try different static type for the parameters, okay? Also, we got some array indexing here. Okay, let's look at one by one. The first question here we already answered. For this SS array, every element has the static type students. So this one here, all the way to the very last, they all have static type students. Okay, that one should be easy to see just by looking at where they are declared. Okay, second question. Let's now look at this particular method here, add rs, where we have this line. Now, the question is, does this line, which is a variable assignments, does it compile? Compiles? How come?
Because you can fulfill the expectation of students from the dynamic type of RS.
When we talk about static type, right? You got to be careful. And also, when you organize the argument here, you want to be a little bit more structured. Okay, I'll show you. Yeah, it's not too bad the way you argue. You want to try for you?
Because resident student is a descendant of student, or student is an ancestor of resident student.
That's true. Yeah. What I will make it even more complete. I want to talk about which one is the static type of which, right? Okay, I'll put it down here. So you want to say RS over here is the parameter. That one has a static type, resident students. And SS at index C is referring to this array. We know that every element, every element there has a static type, students. Now we're asking, basically, is RS a descendant of students? Yes. All right. Okay, so it will compile. Okay. Final line. Let's make it very important, and then we'll do one exercise together. So now, let's assume we have an instance. SMS is an object of type student management system. Student management system. Okay, let's say. And we are calling the add rs method right here. Okay, you can see add rs, add rs. And the argument is O. And the parameter is rs. All right, so now here's a question. I'm going to write it down. Under what conditions will this method call compile? Under what condition? Well, what does this method call compile? Right, it's a question. And I can give you hints. To really judge this one here, you have to think about what's the behind the scene call by value, a variable assignment we're doing. All right, go ahead.
Would it only be descendants of resident students?
What should be a descendant class of resident students? Itself. When you say itself, okay, getting there, okay, you're basically right, about, I would say about 50%. You're saying something should be a descendant class of resident students. And resident student, I know, is the static type for the parameter rs. You're getting that one right. But what exactly is what to start with, right? Okay, huh? Huh?
What's the question?
What's the question here? Under what condition will this compile? And let me just get to it, okay? Yeah. So to really look at this, again, we're going to look at exactly what the call by value will look like. Okay, so here we have the call by value, which is parameter rs equals arguments O. And then we know that rs is declared to be resident students. Static type is resident students. And now we were asking what can be its static type in order to make it compile. The static type will work as long as it can fulfill the expectation of rs of the left-hand side, right? All right. So that means given these two, okay, so this one here, compile, compiles if the question mark, which is a static type, is descendants of resident students. Okay, so that's the answer. And in this case, we have no choice because resident students is already at the bottom here. Its descendant is only itself. So that's the only choice. Okay. It's a bit abstract, but I think it's also concrete somehow, just using example. But let's now try to reinforce the understanding. Okay, let's now take a look at some exercise. Yeah, I think we got time. Okay, that's the final exercise for today. All right, so this is good. And then, okay, let's say this. Let's say we got different variables being declared. And for now, we only talk about compilation. Only compilation. Don't worry about dynamic type. Okay? We got S1, S2, S3. All these have the same static type, students. Their dynamic types are different, but they don't matter. Okay, only static type. Also, we got RS, which has static type, resident students. We got NRS, non-resident students. So we got 5 reference variables with different static type. That's how we start with. And then we have some student management system objects. And let's say now we are trying to call right here. I'll show to you. Okay. So let me start you with right here. We are basically calling add rs, this method here. And then we are basically talking about all these. All right? And the question is, each individual line, is it going to compile or not compile? So think about 1, 2, 3, 4, and 5. And we kind of did that, right? Just in the previous page. But now we're just making it even more concrete about the application context. Does 1 compile? No? I agree, no, but how come? Yeah, on the right track, yeah. Okay, so let's look at the first one. If you look at S1 here, call by value, RS, right? If you look at that, so this one here, call by value, you're actually going to get RS assigned to S1. RS has the static type resident students. S1 has the static type students. Is students a descendant class of resident students? No. So, not going to compile. How about number 2? Yeah, that's exactly the point, right? Even though they're different reference variable, but they have the same static type. So they will compile for the same reason. All right? So S2, S3, they got the same static type. So wouldn't compile. How about number 4? It will compile because in this case, just don't get confused. You got RS and RS over here. They're different RS, right? Different scope. So think about this one here. Let me put orange, right? So call by value is going to be the argument RS is assigned to the parameter RS. And the RS over here has resident students. Static type, resident students. And RS over here has static type, resident students. Resident students on the right-hand side is a descendant class of itself on the left-hand side. So that will compile. Final one. Will not. Because NRS over here statically is a non-resident students, which is not a descendant class of resident students. All right? So that one there, if I do one more, call by value is going to be RS assign NRS, right? It's not going to compile. So now let's make some very quick mini conclusion, and then we do one more, okay? So given this, what can we conclude? You can see the only one that's going to compile. I'm going to highlight in green. This is the only one that's going to compile. What does that really mean? Once you declare your static type of the parameter in any method call, you can only accept the arguments whose static type is the descendant class of the parameter type. And in this case, resident student has only one descendant class itself. Okay, I'll write it down. So, call to this method only compiles if the static type of the arguments is descendants of the static type of parameter, which is resident students. All right, it's a very important insight right here. And let's apply this insight right away, okay? And then we should be good. Okay, guys, let's see one more, okay? The next few. The next one there, we are basically talking about, let me use maybe this, all these. Okay, if you look at those, the parameter that we are talking about is as students. You can see the as students method here has the student declare type. So this is the top of the hierarchy. So now if you look at students, it's at the top. any method call which got the arguments whose static type is a descendant of students is going to compile. In this case, any class will be okay because all the classes are descendants of the top of the hierarchy. All right. Arguments with static type a descendant of students will compile. Okay. And in this case, let's say, for example, S1, S2, S3, they are static type students. Student is a descendant class of itself. Also, when we got RS, resident students, which is a descendant class of students. And also we got NRS over here, non-resident students, a descendant class of students. Right? So all these will compile. Okay? So this means the higher of the hierarchy of the class you choose as a declared static type for the parameter, the more arguments you can actually accept. Okay? That's really the conclusion. So all these will compile. All right, any questions? Yeah, go ahead.
Wouldn't it make more sense, for example, in add RS to check if it's instance of resident student and then cast it to resident student?
Well, instance of is more like a check for class to really avoid class cast exception only. So in this case, you're talking about inside the method, right?
Yeah.
Okay.
Either.
I would say let's kind of separate the layers, right? So guys, 1 minute, and then we'll be done. Okay, bear with me. So whenever you only talk about compilation for the method call, you only worry about the static types for the parameter and the arguments. That's it. Inside the method body, let's say given that, let's say when you say add students, right? I know what you mean. So here, when I say add students, when I make a call to add students, I pass an argument O. Statically, I only require O to be a student statically. But now dynamically, I may require that to be a resident student, in which case, yes, inside the method, I can say O instance of something, and then I can do something else.
I mean, like in score, yeah, you're adding an RS, sorry, no, not one. S2. S2 is a resident student, but you can't, no, in like add RS, S2 is...
Yeah, of course, I'm just saying, but as far as the compilation concerned, that's the rules we talk about. But inside the method body, you might do instance of check if necessary. You may.
To be fair, you shouldn't, because the moment you enter add RS, you have already, the checks have already, either you have compiled or not, and it to be casted to RS.
Let's discuss it maybe after class, okay? So thank you, and then I'll see you tomorrow for the test. But we got review session at 3 p.m. if you want to come.